All right, greetings everyone. So let's practice finding antiderivatives using substitution. Before we begin the actual examples, let's just recall that when we're using substitution, what we're really trying to do is reverse the chain rule. So if we're trying to take the derivative of the function f, the composition f of g of x with respect to x, by applying the chain rule, we would get f prime of g of x times that quantity times g prime of x. And so we should know then, just by reversing this process, if I take the antiderivative of f prime of g of x times g prime of x with respect to x, then I get just back to f of g of x. Of course, we're finding the most general, so I want my plus c. But the question does become how, mechanically. I mean, we're doing that by observation, and the idea of antiderivative being the process of taking a derivative. But what are the mechanics of the substitution for this? The key is that we have an inner function here, g of x, and it's that inner function that didn't come out very well, that we are going to let be, we're going to let our new variable be. We typically use the letter u, but we don't have to use the letter u. We could use any letter that's already in play in some part of the problem. So if I let u equal the inner function g of x, and then I take the derivative of u with respect to x, and we write it in this form here, it's in differential form, then I can see in what's going on, hopefully fairly clearly, that this whole expression g prime of x dx is going to be replaced by du, and then the inner function, as I've already said, g of x is going to be replaced by u, so that I can rewrite the entire integrand in terms of the new variable u. So let me put a little bar here. So if I rewrite this with substituting, I end up with f prime of u, and then the entire expression g prime of x dx is replaced by du. And then I need to find the antiderivative with respect to u of f prime of u. Well, that becomes just f of u, and then of course the most general, so we want a plus a constant. And then if I substitute back in place for u what u is defined as, it's defined as g of x, then I get f of g of x plus a constant, which we now got by just looking at the mechanics of substitution and not looking at the fact that we just took a derivative, so we know what its antiderivative has to be. So that's essentially it, and that in there lies the key of what we're trying to do. So let me just point the key out one last time. So I'm going to ideally find some inner function, typically, or some function in there that I'm going to define as my variable, where the derivative of that inner function is going to be contained in the integrand as a factor, something being multiplied in. And if that pattern is there, then we can try the substitution property or process. Let's take a look at this example. And please pause the video and go try this yourself, and then you can come back and watch my work and see if you agree with it. So here, what I would do is I would let u, or whatever variable I'm choosing, be 1 over x. The reason why I would let u equal 1 over x is, again, I'm looking for an inner function, and that's not the only inner function here. I mean, we have secant being squared, so I could think about letting u equal secant. But if I'm thinking about this clearly, the derivative of secant, which is secant x tangent x, I don't see any tangent functions in here, and so even if that substitution would work, and I'm not sure if it would or not because I haven't tried it, it would be more work than what I'm about to do, because I can already see that there's a process that's going to allow me to get what I'm doing now to work successfully. So continuing, I'm going to take the derivative, and you can think about 1 over x as x to the negative 1 if that helps, which then would give us negative x to the negative 2 dx. But I wouldn't leave it written that way. I would rewrite this as negative 1 over x squared dx. And the reason why I would write it that way, if you can't see it already, and it's okay if you can't, so I'm going to point it out, is you see how I got this dx over x squared here? I got that same relationship here in my integrand, and so I'm going to be able to replace that dx over x squared with the expression du. There's one slight little issue here. I have this negative which isn't anywhere in my integrand, so I'll balance the negative out by letting negative du equal to just 1 over x squared dx. And so I'll put in, I'll balance out that negative sign with that process. So this becomes negative, for the negative I just mentioned, the antiderivative, or the integral of secant squared. I've got to squeeze it in here a little bit. Secant squared. Now 1 over x, we said that was u, so that becomes u. And the dx over x squared gets replaced with that negative du. And so I already got the negative accounted for, so I guess I have to include now the du. All right. Can I find the antiderivative of secant squared u? I hope that you can. We should know that the derivative of tangent is secant squared, and so this becomes negative tangent u. Of course, we're looking for the most general, so don't forget your plus c. And then we just want to leave the final answer in terms of the original variable, so we get negative tangent of 1 over x plus a constant. Now the nice thing about working out these problems on your own is that you can take the derivative of this result and then see if you end up right back where you started. So I'm going to go back to this previous blank screen over here, or almost blank screen except for that little mark. And let's take the derivative with respect to x of negative tangent 1 over x plus c. And let's see if we can get back to where we started. Make sure that negative is clear. All right, so since I'm constant multiple rule, the derivative is just going to be the opposite of that. So bring the negative along for the ride. The derivative of tangent we know is secant squared of the inner function. Okay? And then we have to multiply by the derivative of the inner function. So the derivative of 1 over x is, as we said on the other page, it ends up becoming negative 1 over x squared, or as we said, negative x to the negative 2, which is the same as negative 1 over x squared. The derivative of the constant is 0, and then if I rewrite this or simplify this, I got a negative, got this negative times this negative over here, but let me get rid of those circles, which becomes positive. So we end up with secant squared 1 over x squared, which is exactly the integrand that we started with back on this page, and so I know I've done the process correctly. Here's another example. Again, please pause the video, try to work this one out, and then come back and see how well you did. I'm going to let you, well, I accidentally wrote a w, so I'll let w equal cotangent of x. So that means dw, for all you Arthur fans out there, is negative cosecant squared x dx. And that works out nicely right there, okay, because we have that cosecant squared x there, which is what I need. I do have an extra negative that I have to account for, so I'm going to multiply both sides by a negative to rewrite this negative dw equals cosecant squared x dx. And then I can now make my substitution, and the substitution becomes, or after the substitution, we end up having the negative, which I'll put out in front of the integral, square root of w. I'm a little sloppy right now. I'm sorry. Square root of w dw. And then if you are still struggling with some of your antiderivatives, we can rewrite this as w to the 1/2 power, and then we're going to reverse the power rule. So we need to add 1. The negative is going to go along for the right here. Add 1 to the exponent for the w to get 3/2. And then we have to divide by that new exponent. So we should divide by 3 over 2. But if we know or remember our rules for fractions, which I'm not demonstrating at the moment. Instead of dividing by 3 over 2, I could multiply by 2 over 3, and that's equivalent. And then, of course, plus c. And the last thing I need to do is just go ahead and substitute back in place of w, cotangent of x. So it would be cotangent of x raised to the 3/2 power, all that times negative 2/3, and then, of course, plus c. So that's the answer for that one. And again, you can check by taking the derivative of this result and seeing that we got the integrand above. All right. Go ahead and pause the video and try this one. In the denominator, that's z cubed plus 1. I know it might be a little bit blurry. It is to my eyes right now. All right, so I'm going to let u equal z cubed plus 1. So that I'll get du to equal 3z squared dz. Which is good because I can see that I have a z squared dz. I just have this extra factor of 3, so I'll divide by 3 or multiply by 1/3. And I get 1/3 du is equal to z squared dz. Now I can start making the substitution, and this becomes 1/3 the integral. The z squared dz was the 1/3 du, so I'm just going to put 1 over du. You can put the du in place of the 1. I just like to write it separately myself. And then down here we have u. We should know that the antiderivative of 1 over u becomes the natural log of the absolute value of u. You got that 1/3 still as a factor. We, of course, need our plus c, and then it'll be 1/3 natural log, absolute value of the quantity z cubed plus 1, and then all of that plus a constant. One last example here, definite integral. I may actually put in one more, so that, let's say this is the second to last example. But let's give this one a try. Pause the video and give this a try. So let's let u equal the natural log of x. If I take the derivative, I get du equal to 1 over x dx. This is a nice result because hopefully you can see up here we got the dx over x there, the same dx over x here. So I have my du, and I can replace everything and now be in terms of the variable u instead of the variable x. So we have the integral. I'm not going to put the limits of integration on just yet. Okay, I'll do that in just a minute. So we end up having sine of u du. Again, natural log of x was u, so I plug in u for the natural log of x, and then du for the rest of the dx over x part. Now what about these limits of integration? That still is something that's been a bit of a challenge for some students to deal with. In our original integral, this 1 that we have here is a value of x, because if you look, we have a dx at the end of our expression here. That means we're integrating with respect to x, or along the x-axis. So the number 1 in our lower limit has to be an x value. Same thing for the number e that's in our upper limit. That's an x value. So when I rewrite this now in terms of u, I need u values, not x values, in my upper and lower limits of integration. So I need to make new values so that I can now have values along the u-axis for my limits of integration. So what I'm going to do is I'm going to plug in that 1 in for x here, because 1 is an x value, and we defined u to be the natural log of x. So to find my u value that corresponds to x being 1, I need to take the natural log of 1. Hopefully you know that the natural log of 1 is 0, so my new lower limit is going to be 0. And then I'm going to do the same thing. I'm going to plug in the e for x over here as well, because e is an x value. And I'll get the natural log of e, which hopefully, again, you know is 1. And so my new definite integral is the definite integral from 0 to 1 of sine u du. And now I can go back and finish solving the problem. So when I take the antiderivative of sine of u, I get negative cosine of u. Remember, taking an antiderivative, so the derivative of sine is cosine, the antiderivative of sine is negative cosine. And then we're going to evaluate this from 0 to 1. We don't need a constant of integration here because it is a definite integral, and it would subtract in the difference when we're applying our fundamental theorem here anyway. So this becomes negative cosine of 1 minus negative cosine of 0. Cosine of 1 is a value. I don't even know what cosine of 1 is. I could look it up on a calculator if I wanted, but I'm not going to. Cosine of 0, however, we should all know that that is 1, so this is minus a negative 1, which of course would be a plus 1. So the answer to this is negative cosine of 1 plus 1. Hopefully you got that as well. I'm going to pause and go find a new problem for you guys. Alright, so here's one last example to try, so pause the video and go give it a shot. So I'm going to let u equal the square root of x. That is an inner function that I have here, and I can already see through my experience that I'm going to have the derivative in there as a factor. So when I take the derivative, remember square root of x is x to the 1/2 power, and if we apply the power rule, we get 1/2 x to the negative 1/2, and we're in this form here, so put dx. And then if I rewrite this with a negative exponent, or rather without the negative exponent, this is 1 over 2 root x dx, which is kind of nice, except for the fact that I have this 2 that's in the denominator in my result at the bottom, but wasn't in the original integrand. I'm going to have to balance that out. That's not a big deal. We've been balancing those out already anyway. So 2 du will replace the 1 over root x dx. And so just again to highlight this and point out what's going on, the dx over square root of x in the expression on top is the same as what we have over here, so I'll replace that with 2 du. Alright, so let's see if we can finish this here. So I need that extra factor of 2, which I'm going to put in the as a constant multiple. The limits of integration I'll switch in just a moment. I know I'm going to have a du that was replacing the dx over root x, and along with the 2. And then what's left is the e to the root x, which becomes just e to the u. And then again, I need to rewrite in terms of some new limits of integration, because this was done before in terms of x. Now it's done in terms of u. So I need to plug in the 1 and take the square root of 1, which is still 1, so it's the same lower limit, but that's by coincidence. Then I'll plug in the 4 and for x over here, and the square root of 4 is 2, and so my new upper limit of integration will be 2. And so when I work this out, I get 2. Then we're going to find an antiderivative of e to the u, which is just itself. No constant needed here. You can evaluate that from 1 to 2. So this is going to be 2e squared minus e to the first power, which then doesn't need to be simplified any further. Really, there's no useful simplification, so we'll let that be the final answer that we get here. And hopefully you got that answer, and you understand how to do substitutions much more clearly than before. Go study.